Hello students, welcome back to my 5th lecture on basic maths. In our previous class, we studied the first part in number theory. We found least common multiplier, highest common factor of numbers with relation between them using the formulae. Now, we shall study second part in number theory, that is rational numbers, irrational numbers, real numbers, complex numbers with their properties one by one. So let's get started with rational numbers. So as you are already familiar with the fraction, that is written in the simplest form as P upon Q, where P and Q are integers and Q should not be equals to 0. That is called as a rational number. A number in the simplest form P upon Q is called as a rational number and it is denoted by the capital letter Q. For example, 4 upon 7, 3 upon 5, minus 2 upon 3, etc. Such numbers are rational numbers. Note here that every integer is a rational number. Yes or no? Every integer, that is, if you write only 2 upon 1, it is in the form of P upon Q. Fine. Second one, 0 is also a rational number since we will write 0 is equals to 0 by 1. It is in the form of P upon Q, where P and Q are integers, Q is not equals to 0. Third note, square root of a positive integer which is a perfect square is also a rational number. For example, square root of 16 is equals to 4, square root of 25 is equals to 5. Why? Because 4 can be written as 4 upon 1. It is in the form of P by Q. Fourth note, all rational numbers when expressed in decimal form are either terminating decimal or recurring decimal. What do you mean by terminating decimal and recurring decimal? We will see in the next slide. For example, see, terminating decimal example is here. 2 upon 5, when you divide 2 by 5, you get 0 decimal 4. Here, when you divide 2 by 5, remainder will be 0. So, it is a terminating decimal. Next example, 1 upon 3 is equals to, if you divide 1 by 3, you get 0.333, so on. It continues, no remainder. Sorry, with every time remainder will remain only, is a non-terminating recurring decimal. So, non-terminating recurring decimal in the sense, the number after decimal, the number is repeating, the same number is repeating. So, it is called as a recurring. Recurring in the sense, the same number is repeating. And it remainder will remain only, the process will continue, so on. Hence, it is non-terminating recurring decimal. So, next example comes, express each of the following rational numbers as decimals. They have asked just to find the express in the form of rational numbers as decimals. So, just divide and keep it up. 3 by 4 is equals to 0.75. 15 upon 8 is expressed as 1.875. So, here the definition of recurring decimal comes, a decimal representation in which all the digits after a certain stage are repeated. I will repeat, see, A decimal representation in which all the digits after a certain stage are repeated is called as a recurring decimal. See the previous example. 1 by 3, if you divide it, you get 0.33, so on. 3 will continue every time. The same number is continuing. So it is also can be written as 0. Instead of writing 3 again and again, you can write simply 3 bar. 0.3 bar. Up there is a line just above the number 3. Now next one, mixed recurring decimal. A decimal in which some digits after the decimal point is not repeated and then some digit or digits are repeated is called a mixed recurring decimal. Here mixed itself means the numbers are different. That is, here in example 6.1255 is there. So here after decimal there is a number 1, 2, 5. Only 5 is repeating. So here numbers are mixed in the form of mixed recurring. Therefore, here you can write it as 6.125 bar. Only 5 is repeating. So write down bar over there on 5. Note here that let x is equals to p upon q be a rational number such that prime factorization of q is of the form 2 raised to n into 5 raised to m. Then decimal expansion of p upon q terminates. Here the note of first one says that to get whether the rational number is terminating or no, you just have to check the denominator. It should be after prime factorization, the number must be in the form of 2 raised to n into 5 raised to m. Fine, we will see this with the example afterwards. Second one, if p upon q is a rational number such that prime factorization of q is not of the form of 2 raised to n into 5 raised to n m, then decimal expansion of p upon q is non-terminating. If the number is not in the form of 2 raised to n into 5 raised to m, then it is obviously called as non-terminating. If it is in the form of 2 raised to n, denominator is in the form of 2 raised to n into 5 raised to m, then such rational numbers are called as terminates. Otherwise, it is called as non-terminating. Okay, we will check these clarification with one example. Without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. First example, 17 upon 3125. Here p is equals to numerator, that is 17, q is equals to 3125, that is a denominator. Just check the denominator, find the prime factorization. So here 3125 has its prime factorization as 5 raised to 5. 5 raised to 5 is nothing but 3125. So it is in the form of 2 raised to 0 into 5 raised to 5. Here we have just compared 2 raised to n with 2 raised to 0, as the value of 2 raised to 0 is 1 and 5 raised to 5. Compare, it is in the form of 2 raised to n into 5 raised to m, hence it is a after expansion, after division, the number is in the form of terminating. So it is called as a rational number having decimal expansion. We will move towards the next two examples. 13 upon 8. Find the prime factorization of the denominator 8, that is equals to 2 cube. 2 cube is again in the form of 2 raised to m into 5 raised to n form. So in previous sum, by definition they have taken 2 raised to n and 5 raised to m. Both are same. Just m and n are its indices form, exponents. How many times a number is repeated. Therefore, 13 upon 8 is a rational number having decimal expansion. Next, 31 upon 243. Prime factorization of 243 is equals to 3 raised to 5. It is not of the form of 2 raised to 5, 2 raised to m into 5 raised to n. Why? Because the base is 3 here. The base must be in the form of either 2 or 5. But here it is 3. Hence, the number is non-terminating decimal expansion. Next, come to the new concept, that is irrational numbers. A number which cannot be put in the form of p by q, where p and q are integers and q is not equals to 0, is called an irrational numbers. Simply, a number which is not rational is irrational. For example, root 2, root 3, root 5, root 7, etc. are called as irrational numbers. Note here that negative of an irrational number is an irrational number. That is, for example, minus root 2. It is also a rational number only. Second one, sum of rational and irrational number is always an irrational number. For example, 2. 2 here is a rational number plus root 3. Root 3 here is an irrational number. If you add rational and irrational number, you get again an irrational number only. Third note, product of a non-zero rational number and an irrational number is irrational only. How sum and difference becomes irrational? Similarly, product also becomes irrational. Product of non-zero rational number, that is 2 by 3, into irrational number, that is root 3 plus 1, also becomes an irrational number only. We will prove some examples. That is, first example, prove that root 2 is an irrational number. So here we shall prove it by contradiction method. If possible, let take root 2 be a rational number. So equate it to p upon q, that is a rational number where p and q are integers and q is not equals to 0. Further, let p and q are primes, co-prime, that is HCF of p and q is equals to 1. Now further simplification, root 2 is equals to p by q, cross multiply q with t with root 2, that is root 2 into q is equals to p. Now taking squaring both the sides, we get root 2. When you square root 2, you get 2. Then q square will be equal to p square. Here 2 divides p square, that means 2 also divides p. Once it divides by p, then it means p is an even. Now let p is equals to 2k, where k is any integer. Then p square will be equals to 4 into k square. Now substitute the value of p square, that is equals to 2 into q square, which is equals to 4k square. Then 2 will get cancelled with 4. 2 ones are 2, 2 twos are 4 to both the sides. Then remains q square is equals to 2 into k square. Again q square here is a divisible by 2, hence q square is even, then q is also even. Now p is even, q is also even, which implies p and q have a common factor, which is a contradiction of the fact that p and q are co-prime. Therefore, our assumption that root 2 is rational is wrong. Therefore, root 2 is an irrational number. Next example, prove that 3 plus root 5 is an irrational number. So, take, if possible, let 3 plus root 5 be a rational number. So, compare this rational number with a by p, a upon b, where a and b are integers and denominator b is not equals to 0. Shift 3 to RHS with minus sign, a upon b minus 3. Root 5 is equated to a upon b minus 3, and here a upon b is rational number, minus 3 is also rational number. If you subtract rational number to rational number, you get again rational number only. Hence, irrational number root 5 is equals to rational number. Is it equal to rational number? Irrational number is not equal to rational number. Hence, our assumption is wrong. Hence, 3 plus root 5 is an irrational number. So, this is an exercise 1.4. They will ask such questions for 5 marks. Prove that root 2 is an irrational number. Root 5 is an irrational number. Same way, just change the number and write the related data. Prove that 2 plus root 3 is an irrational number. Prove that 2 plus 3 into root 5 is an irrational number. Similar way you have to follow the steps. Fine. Next question, 2 marks question. Without actual performing the long division, you have to show the following fractions as terminating decimal or non-terminating decimal with the trick, that is, check the denominator whether it is in the form of 2 raised to n into 5 raised to m. Okay, we have done already these sums in this class itself. You just go through that sums and follow the same process. So with this exercise I conclude. We will meet in the next class with new concept, that is complex numbers. Till then, you just maintain the fair book and study. Okay, thank you.